So, we discussed that for many applications we need alternating current source which can give us some kind of a waveform where the voltage changes periodically with time at a desired frequency, and that kind of voltage signal is created by circuits which are called oscillator circuits. The essentials we had discussed. The essentials parts are that you have some kind of a frequency selective circuit, also sometimes known as frequency selective filters, and what we discussed was this LC oscillations, LC circuit, which is used for several tens of or hundreds of kilohertz onwards up to say megahertz, like that. So, that kind of a tuning circuit which can oscillate at one particular frequency, and that is decided by the parameters here. And then the voltage goes to an amplifier, and this is where the transistor comes into picture. This goes to an amplifier, and then from the amplifier you take your output also, and then you have a feedback mechanism. And this feedback circuit then gives signal. Whatever is lost here is compensated here, and therefore a positive feedback that means the phase of this voltage which is there and the phase of this voltage which is coming, they should match with each other so that the losses are compensated, the amplitudes are added, and you get a supply of constant AC voltage. So, there are various ways, lots of circuits are there. We will be describing one or two. The first one is called tuned collector oscillator. So, in the amplifier you have a base, emitter and collector, and it is the collector which is connected to this tuned circuit, and therefore it is known as tuned collector oscillator. So, let me revise little bit of this amplifier, how we use transistor as an amplifier in common emitter mode, and then we will see how to put up these things. So, in a transistor amplifier we had in common emitter configuration, you have this emitter here and collector here, base here. Then you put this to ground, some resistance. In actual case you also put some capacitor, so that this alternating things is bypassed from here. And then this side should be forward biased, and this is NPN transistor, so this should be forward biased. So, we put up a resistance RC, and then the bias voltage here like this. So, this, and on this side we have this RB resistance, and then we put biasing voltage once again here. So, this is the basic configuration of this amplifier. This we had discussed in detail. There are some more modification, but basically this is the thing. Now, at this stage I would like to introduce two things. One is another way of writing these things. For example, if this RC is connected to this VCC here, this point is 0, this is all 0 potential, which we call ground. The ground itself is represented by the symbol of ground. So, what you can do is, this point is just ground, This point is just ground, and this point RCC is connected to this VCC. So you can just remove all these things from here, and if you just write that this point is VCC, it serves. It tells me that with respect to this ground, this point is at this potential. So a battery is connected between the ground and this VCC is there. So that's one thing. This is how you can do many things. For example, this RB here, this is VBB base. So instead of writing in this fashion, what you can do is you can just remove it, and you can just write it that this is VBB. So that means we know that okay, there is some battery connected here and is maintained at this potential with respect to this ground. And then you can remove this ground line also. You can remove this ground line also, and these things which are connected to ground, this also you can remove, and you can put a ground symbol here. You can say that this is ground, this is the ground symbol, this is ground. Wherever there is a zero potential point, you can put this symbol anywhere in the whole circuit, and we know that that is connected to this line. So this is one thing. So let me redraw it, only the geometry. Let me say that this is this RC, I will write like this. In books you can see these kind of diagrams, that is why I am telling VCC. So this goes to RC and that goes to VCC. So this point and this point we have connected this biasing batteries here. That's one thing. Another thing is, instead of using two biasing batteries, one for this collector side and one for this base side, generally only one battery is used, that is this VCC, and from here only a part of it is taken to the base. So that configuration is from here you make some kind of a potential divider. You take a resistance R1 and a resistance R2, and this is at ground. So you can connect it, or you can just write this way. This is also okay with us. This is also okay with us, or you wish you can connect all these things and make a line. That is also all right. But somewhere you have to, you should say that this is the ground line. So this is that ground. And then this VCC is falling on this R1 and R2, and then from here we can take to the base. In that case, I am not using another battery. That VBB is taken from this potential divider itself. So this whole thing is VCC, and then part of it is here, part of it is here, and this part is going into this. Another capacitor people put, that is for filtering out undesired AC. So this is a kind of amplifier circuit which is there. Now for putting that tuned circuit, where do I put the tuned circuit? So it is the collector, it is tuned collector. So this circuit, this tuning part, that oscillating part will be in this portion. So the circuit will be modified little bit. And here it goes to let us say a capacitor here, and then you have this inductance here. You have this inductance here. So this is that LC circuit. This is that LC circuit, tuned circuit, frequency selective circuit, also known as tank circuit or tank. Tank we use to store water or oil or food grains or something which is stored that is tank. So here it stores the frequency or the amplitude, so known as tank. So here we are putting that into the collector circuit, and this L which is here, it is actually the primary of a transformer. Okay. So remember transformer, you have a core, and on that core the windings are there, two windings are there, one is called primary and one is called secondary. Then on primary side you supply some voltage, AC voltage, and this AC voltage drives current, and that current produces magnetic field, and since it is through that same core, whatever soft iron or core, so that magnetic field also reaches here, a flux is generated. Since it is varying with time, this flux also changes with time, and then you have a voltage induced here. Then you have all that mutual inductance, all those mathematics can be done. So you produce a voltage here, and the ratio can be determined. How much voltage is here and how much voltage is here, that is determined by the number of turns here and number of turns here. And the symbol for this is, you draw two vertical lines, and then you draw the primary, you show the primary here and you show the secondary here. So this is the symbol. These two vertical lines represent that core, which is the bridge for sharing magnetic field between this coil and this coil. Through this ferromagnetic thing, the magnetic field lines are guided, and you have this. So that is the symbol. So we put the symbol here. This is that transformer primary. This one is that primary. And then you have secondary, and number of turns you can decide, and also the way it is, these windings are done. And this you can collect in this base circuit. So the tuned circuit is there. This is the tuned circuit. It will oscillate at a particular frequency, resonance at this particular frequency, and then this whatever voltage is generated, it is coupled to this second coil. If you call this L1, this is L2, so it is coupled to this secondary, and this we are bringing back here. So whatever was going through this biasing to the base, in the path we have connected this. So part of this output which is generated, this amplified thing which is generated, is taken into this base circuit. So if you look at this, you can use your output also. You can use your output from here, V out. And when I write V out here, that means this the voltage is taken from here with reference to the ground. So this is, I could have written, I can put line here and they say that here is the output, but writing V out itself means that this is with reference to this ground line. Okay. So the amplifier is putting its contribution here. So whatever is lost, whatever is gone is compensated from here. This amplifier is giving signal into it, and what it is amplifying? It is amplifying this signal. So we are not giving anything from outside. From outside we are not giving any AC signal. It is only this AC signal which is coming and which is going into it. So that is how that tuned circuit, and this is that feedback network, feedback circuit, and this is that amplifier. So all those three blocks in the diagram, they are implemented in this fashion. And how do we ensure that the phases are correct? Okay. So whatever is the oscillations here, from here when this transformer primary secondary, that coupling is made, then the winding, direction of winding ensures that there is a 180 degrees of phase change between this part and this part. So there is a 180 degrees of phase change, and then when this signal goes here and gets amplified, so you remember that in common emitter configuration, when this amplification takes place, then you have, by the way, I have not connected this thing to this circuit, you have to connect it here. So let us put a resistance and then connect it, so that this whole circuit has to be completed anyway. So yeah, so in that common emitter mode, when you do amplification, then the phase of the output signal and the input signal, they differ by pi, right? Because if this base biasing, this voltage increases and current increases, then on the other side the current in the collector circuit increases, and then the output voltage goes down. So there is a phase change of pi here, okay, here there is a phase change of pi, and then here again there is a phase change of pi from here to here, right, from here to here, from this base to this collector here, again phase change of pi. So twice this circuit is giving its output for feedback, and the phase change of pi is introduced here because of the transformer action, and then when it gets amplified and comes back here, another phase change of pi, and therefore what reaches here, it's same as what it is there at that moment. Okay, so this is how that positive feedback is ensured. So when the circuit is put on for the first time, wherever you have switch, okay, you can have a switch here. So initially there is no VCC, there is only one battery, so that means there is no biasing anywhere. If this switch is open, if I say that this VCC, I put a switch here and this VCC is open, that means this VCC means you have a battery out here, you have a battery out here. That's the meaning of this VCC, this VCC. So I can put a switch here. So if this switch is not closed, this battery is ineffective, and that means there is no current, nothing, no biasing, this is just on the table. So when you switch on the circuit for the first time, what will happen? Some current will flow. And if some current will flow, then something will happen, transistor will go into its active mode, and something will be amplified, whatever, so noise or that. But then when that reaches here, that noise or that random voltage change, right, when you switch on, the current starts, and then something goes there, something is amplified, some voltage goes there. So that is some kind of a random voltage change there, and that you can understand as a superposition of sine functions of various frequencies. Okay. Say a sine wave is just like this, or sine function is just like this. It has a definite frequency. But if you take this is, let us say, omega 1, angular frequency omega 1. If you take various angular frequencies and adjust your amplitudes also properly, this is, say, omega 2, you have some omega 3 also, you have some omega 4 also. large number of appropriately chosen frequencies and appropriately chosen amplitudes. If you add all these things, you can produce varieties of waveforms. Like for example, you can produce this kind of thing. This can be taken as this plus this plus this plus this plus this plus this. So any kind of shape can be decomposed into a summation of sine waves with different frequencies and different amplitudes. What frequencies are chosen and what are the corresponding amplitudes, that will decide what kind of final shape appears. So whatever it is, that random voltage change when you first switch on, that can be taken as a superposition of sine functions of various frequencies. But then this is a circuit where if the input going into it is at this frequency, then it oscillates with larger amplitudes. And if other frequencies come which are far away from this, very different from this, those oscillations are of very small amplitudes. So it is selecting out of this many frequencies which are there, it is selecting its own frequency, and that component will get enhanced again and again, and the remaining will die out. So after a very short time, this other components, they all die out, and finally there is only one component, and that is this, and then you have your cycle, and then you get your output with that kind of voltage. And how much feedback is taken, that can be adjusted from this L2. So number of turns here will determine what fraction of this is taken as the feedback. So essentially we need a constant amplitude at the end of it. If this feedback is more than that, then also we are in trouble. If it is less than that, then also we are in trouble. So this number of turns had to be chosen judiciously so that a particular amplitude is maintained. So this is how an oscillator works, and this is the circuit for that tuned collector oscillator, normally used in radios, transistor radios. So this is also called local radio oscillator. So this is it. Now there are other varieties of these oscillators. One very common is called Hartley oscillators. I will just give you the diagram of that. So Hartley, this is the name of the engineer who had designed it, American engineer, way back in 1915, but is still useful. So this, in this you have that circuit, amplifying circuit, and in the collector part you put that tuned circuit where you have this capacitance, and then on that L side, inductor side, you generally have two inductors, L1 and L2. They may be wound on the same core, so they can be coupled with each other, or they can be separate also. So this L1 and this L2, and then you have your usual some RC and some VCC here, and from that VCC you make that potential divider. So R1, R2, R1, R2, and then from here you give this biasing to the base, and this is coupled the center is grounded. The center, that means the junction of this L1 and L2, that is grounded. And this L2 which is here, this one, this point here, the voltage here, that is taken and joined to the base voltage, base biasing. This is just a capacitor. Okay, so it goes like this. So this is the kind of circuit of Hartley oscillator. And these two separate L1 and L2, one can have a single inductor also, and from somewhere in between you tap it and put it in ground. So the feedback is coming from here, and your output can come from here. This can be the output point. Right, so that feedback is coming from here. This is at ground potential, at zero potential, this potential, and then this point which is at some voltage which is changing in time, that is joined to this biasing of base. So that is the feedback network. So this is one design which works quite well, and the phase relationship is once again, if this is grounded and if the current is going in particular direction, so at certain time when this is positive, then this is negative. So a phase change of pi by 2 is ensured here, not pi by 2, pi is ensured here, and then another phase change is here. So when this gets the signal, it gets in the same phase. So that is how it is done. Closely related is Colpitt's oscillator. So once again the same story. The only difference is that instead of 2 inductors and 1 capacitor, this circuit will have 1 inductor and 2 capacitors. Okay, so I can just modify this design itself. You will have an inductor here, and you will have 2 capacitors here. So you have an inductor here, this is L, and then you have 2 capacitors here, C1 and C2. So this also works well. This is known as Colpitt's oscillator. The resonant frequency in the case of Hartley, which is square root 1 over LC, and this L which was there, you had 2 of them, L1 and L2. You had 2 of them, L1 and L2. So L is equal to L1 plus L2 and plus the mutual inductance. So if there is a coupling between these two, which will happen if they are made on the same core, so that any magnetic field which is created because of that current easily reaches here. In that case, you will have a good mutual inductance, and then this must be taken into account. And if they are on separate cores, so that the magnetic field diverges out of core and not much reaches here, then this mutual inductance will be very small, and L equal to L1 plus L2 can be worked. And in case of this Colpitt's, the resistances are there, the capacitances are there in series. So here again the same story, but then C has to be the series combination. So it will be C1 C2 and then divided by C1 plus C2 and whatever L is there. So this is how these things are determined. And how much will be the feedback, what fraction will go into the feedback, so that again is decided by this ratio C1 and C2, and for Hartley this ratio L1 and L2, because the same current is going. So the part which is here, which is going into feedback, and the part here which is going into the output, so that fraction will be just this ratio of L1 and L2, and similarly here that fraction will be the C1 and ratio of this C1 and C2, because the is the same. Once again, they are series connection, so depending on what the reactances are, so that fraction voltage will be here and that fraction of voltage will be there. These are all AC things that we are talking. Okay, so when you use 1 over C omega, L omega, those things will be operative. So this is how the oscillators are generally made. So I'll stop here, and we will start our last phase of this course, and that will be digital electronics.